We will discuss about the nullity, rank, and the fundamental theorem of a matrix in a space, or fundamental theorem of a linear algebra, which is the very important theorem regarding that directions. So also we will discuss some problems related to the assignment number 5. We will start first of all from the topic of the book, as we already saw last time, the coordinate vectors. So coordinate vectors are the important vectors, and these are actually just the scalar multiples of a vectors. For example, if v is any vector and v1, v2, v3 are the vector from the basis set, then the c1, c2, c3, these are called the coordinate vectors to s relative to the vector v. For instance, if we have these vectors and we want to find the coordinate vector of V5 relative to the basis set V1, V2, V3, then we need to write V as a linear combination of a C1 V1 plus C2 V2 plus C3 V3. Then such a constant, if we find these scalars C1, C2, C3 and just write them in the form of a vector, then such a vector a basis is called a coordinate vector of a given vector. For instance, here we can find of that one. So similarly, this kind of one problem is related to here in the assignment problems. For instance, here you can see that in case of a vector space, for instance, we have the polynomial. We know the polynomial of a degree 2 is a vector space. The collection of all polynomials of degree 2 is a vector space. And suppose that P1, P2, P3, these are the bases for a polynomial of degree 2, because it's a vector space. Then find the coordinated vectors P relative to this basis at P1, P2, P3. So here you just need to write P as a P equal to C1, C1 P1 plus C2 P2 and plus C3 P3. Then need to find the values of a C1, C2, C3. And that C1, C2, C3 will gives you another vector which is called the coordinate vector of PS, which is called the coordinate vector of P, and it's noted with P bracket S, like as this is the representation of a coordinate vectors. But in case of a, like we know that if we have a some straightforward the polynomial and under the standard basis, because the basis, if the bases are standard, then such a constant, like I'm asking here, if you have any polynomial, and we know that 1x, x square, x cube up to xn, these are the bases, standard basis, because they are independent. 1x, x square, x cube up to xn, these all are independent, and they can span every polynomial of degree n. So such a c0, c1, c2 up to cn, these are the coordinate vectors of ps, polynomial degree of n. But whenever they are not standard basis, like at this example, then what you need to do is that you just need to take p equal to c1 P1 plus C2 P2 plus C3 P3, and then need to solve these equations and need to figure out the values of a C1, C2, C3 and write them as a vector. So that vector is called the coordinate vector of P. The next thing is about the rank and also the dimension. We need to be discuss about these things, but first, as we know about the dimension, so as the base in a basis set, the number of elements or number of vectors in the basis set is called the dimension. So here the problem is the same as we have already done about that one. So here just recall that we know that what is the basis. Bases are actually the collection of vectors which are independent and can span the whole space. So the all finite dimensional vector spaces, we have some basis set for which they can generate, and they are independent to each other. So the number of, since we know that dimension here is actually the finite, in a finite dimensional vector space, the dimension of V is denoted with dim V, and this is actually a number of a vector in a basis set for V. In addition, zero vector space is defined have a zero dimension, because in a zero vector, because we know that zero vector, if we take a set having only the zero, then it's still a vector space, and the dimension of that vector space is zero. the dimension space of R set of all real number is 1, because one element is sufficient to generate all of that one is. But in a P2, or in a like in R2, the dimension of R2 is 2, because there are two vectors, and the standard base in the basis set, like the standard bases are 1 0 and 0 1. As we know that every vector space have many basis sets. But the standard, there is someone which are standard. Similarly, in Pn, the dimension of Pn is n plus 1. So there are n plus 1 polynomials required to generate the every polynomial of degree n. And the dimension of M, all matrices of M cross n is M multiplied by n. So if it means that if we have a 2 cross 3 metric, the class of all 2 cross 3 matrix, we require 2 multiplied by 3, 6 matrices, where we can generate every element of a 2 cross 3 matrices, because the 2 cross is a matrix, class of all 2 cross 3 matrix, it's itself a vector space. So these are about the dimensions, and you know that dimension is actually the number of vectors in the basis set of a vector space. The dimension is like in a finite dimensional spaces, the dimension is finite. But if there are some vector spaces who have no dimension, or dimension is equal to infinity. For example, set of all functions. Set of all functions is a vector space, because sum of two functions is a function, zero function is a function, and if we scalar multiply with any vector, any function, then it still becomes a function. So set of all functions uh, satisfies the set of all real valued functions. The class of all set real valued functions is a vector space, but the dimension is infinity for that one, because there are no finite number of vectors or finite number of functions that can generate all kind of functions, because we know that the class of all functions are distinct. For some are the polynomial functions, some are the exponential functions, some are the trigonometric functions like sine, cos, x, some are the logarithmic functions, like in the form of a log of it, some have some log, some basis of that. So similarly, the class of all continuous functions is also a vector space, but its dimension is infinity. Or we cannot say about the basis of a set of all continuous functions. Similarly, the set of all differentiable function is a vector space, but its dimension is infinity, because it's an infinite dimensional vector. These are infinite dimensional vector spaces. Similarly, the space of sequences, we know that sum of two sequence is a set whose function domain is set of natural number. We know that there are many sequences, some are convergent sequence, some are divergent sequence. This class of all sequences uh, makes a vector space, but its dimension is infinity. Like the class of all sequences is infinite dimensional vector space. Infinite. When dimension is infinite, it means it's an infinite dimensional vector space. In this course, our work is mostly related on the finite dimensional vector spaces. You know, the sum of two functions, two sequences is a sequence. If you multiply any sequence with some real number, then you can get another sequence. So the sequence class of all sequences satisfies the conditions of a vector space. So, but we cannot find it basis set, like how many finite number of elements are required to generate the all sequences. So that's why we call it have a no basis. When it have no basis, then it means the dimension of a that basis is infinity. The dimension of a space of all sequences is infinity. And there are also many other spaces in the literatures of mathematics which have some basis, sorry, which are infinite dimensional vector spaces and have no basis. Some examples, I told you that the space of all continuous functions, space of all functions, simple functions of real numbers, space of all complex functions is a vector space, space of all the uh, sequences, the space of all sequences mean collection of all sequences, either zero sequence, convergent, divergent sequences, so whatever, if you collect all the sequences, so that's make a space. but these are infinite dimensional vector space, and the dimension of that space is denoted as a infinity. But the finite dimensional vector space like Rn has a basis, finite basis. So in R2, the bases are 2, for example, and similarly, polynomial of degree 2. These are the n plus 1, like 2 plus 1, 3, three-dimensional, because the constant generating for the constant, and generating for the coefficients of x, and generating from the coefficient of x square. So that's make the three elements at least for that. So standard basis has n plus 1 vectors. So normally sometimes we can calculate this from their standard basis. And because standard bases are easy and easy to compute, and it's easily shows all the details. The next thing is the dimension of a solution space. This is also the very important and interesting problem. Like if you have any linear system, homogeneous linear system, if you find its solution, the solution set of that system is also a vector space. This is the very interesting thing. And if its solution is a vector space, finite dimensional vector space, then it must have some basis. And the number of element of basis is always a dimension. So we can also figure out the dimension. For example, if we solve this by any method, then we can get its solution. Whatever it is, either you can backward solution or substitute by backward value, or take its direct. So still you can get some form of its solution. And when you write it as a linear combination in the element of s plus t or t plus s, so you can get the two elements. There are, you will exactly get the two vectors in all the cases, either backward substitution or whatever the substitution you can using. uh, so then it means there are the two independent vectors. They are generating the solutions of this space. And hence, we conclude that the dimension of a solution space of a homogeneous system is 2, because it has a dimension is 2. And one thing very important, that solution of a homogeneous system is a, since it's a vector space, so solution is called null space, because the solution of a homogeneous system is a vector space, and we call it a null space. And of a the dimension of a homogeneous system, the solution space of a homogeneous system is called nullity. So this is the important word and the short word. Nullity is what? The dimension of a solution space of homogeneous system. The homogeneous solution of homogeneous system, it's itself a vector space or subspace, and it's the solution space is called null space, and its dimension is called nullity. So this is the important words we have used. So on the base of that, so we have some important results of a linear algebra, which is also called the fundamental theorem of a linear algebra, which is based on the nullity plus rank. We will discuss this in today's lesson. So here we can also see the dimension of a solution space of a homogeneous system. So we just need to find out the solution of that. So there are the many ways. So sometimes we can get only the zero solution. Then it's still a vector space of a zero vector is a vector space if you write it in the form of a set. And if they are not, then still you can write as a linear combinations of that one. So if there are three vectors, it's mean the null space is this is a null space, and it has these three elements which are the basis of that, because all the solutions will be generated with these vectors, whatever you put the values of that one. If you put r equal to 0, s equal to 0, t equal to 0, then it will give you 0, 0, 0, 0, 0, 0 vector. And that is the solution of this homogeneous system. And similarly, if you put any other value, or in the case of r, s, and t, then still you can get a solution. So the solution will be based on these three vectors. So the bases are these three vectors, and dimension is 3. So we call it the nullity of nullity means the solution of this homogeneous system, which is a vector space. So we call it a null space. So null space have a nullity 3, because dimension is 3. Null space dimension is 3. So we call its nullity is 3, or sometimes we call its dimension. The general word is dimension of 3, but in shortcut we call its nullity. Okay, so then there are some plus minus theorem related to that. If you add some vectors, and then how it will be it's plays the some effect on that one is. So you can read this from over here. And then also there are some questions that are available in the exercise, and also these are some short questions related to that one, which you can study. And I think we already described such kind of things in the previous lessons, where we can describe that if like V is a vector space, W is a subspace, then dimension of subspace can be equal to W, and or subspace of a dimension of a subspace is always less than or equal to dimension of a vector space. So dimension of subspace is always less than dimension of a vector space which contains its that. And if both are equal, then dimension of V is equal to dimension of U, mean both can be generated with the same number of vectors in the basis set. Um, then so this is about that one, and you have some here the things that just recall that zero vector space has a dimension 0, and there is a 17 linearly independent vectors in R17. Yes, because the basis of R17 is 17. So the 11 vectors can span R17. No, at least uh, at least 17 vectors required to generate the R17 that can span R17. So not 11, 17 should be at least 17. So every linearly independent set have 5 vectors in R5 is a basis, a a basis for R5. So linearly independent set of R5 is fine, because if they're linearly independent, then they can span R5 as well, because if they are independent and the dimension is 5 and they are 5 vectors, so then it means they are also spanning the R5, hence it will becomes basis. So the D part is true, and the set of 5 vectors that span R5 is a basis for R5. The set of 5 vectors that span R5, yes, this is also true, because this is the inverse of that problem. If the 5 vectors can span R5, then it means these 5 are also independent. So there is one result which we already saw in the previous lesson. So every vector that spans Rn contains a basis for Rn. Um, every set of vectors that span, yes, if the set span Rn, then it has a basis for Rn as well. Moreover, every linearly independent set of vectors in Rn is contained in some basis for Rn. If you have a linearly independent set of vectors in Rn, then theirs contains some basis, but it contains all the basis elements of Rn. Because if it has a linearly independent set, but there are two things: that if the independent set is small, then if the independent set is small, then it cannot be become a basis. Then in that case, it contains some elements from the basis set. So in that case, this statement is true. There is a basis for M2 cross. There is a basis for M2 cross 2 matrices, like whose dimension is 5. If dimension is 4, 2 multiplied by, consisting of invertible matrices. Uh, like in the basis set, if we saw that if they are basis, then they must be linearly independent. So, but uh, so it's not always the invertible, because all 2 matrices are the matrices like zero matrix of two rows and 2 columns, which is not invertible. So, but the the invertible and non-invertible matrices are also containing the M2 cross 2. So in the basis set, they can be they can be uh, the invertible or non-invertible. So in that sense, the statement is not correct. If A is n cross n matrices, and I n a square a n are the distances matrices, these are all the distinct, then these is linearly independent, linearly independent. Like one can see that if A is a like 2 cross 2 matrix, and we are asking about the elements of that one, so which are distinct, like distinct to each other. It doesn't means that like 0 0 is also distinct with that, but it will not be linearly independent. If there is a zero matrix in anywhere, maybe in a last one, if you will, if A is a metric, but A square can become 0 of that one. So if you have that metric, then in that case, they will not become the linearly independent. And there are at least two distinct three-dimensional subspaces of P2. Yes, in a like P0, P1 are the subspaces which are distinct, and there are two distinct three-dimensional subspaces. Three-dimensional means we can say that these are the the independent, and we need to be check it that which of that twos are linearly independent, because if there are three-dimensional, then because P2 has a three-dimensional subspaces. Uh, but they can be distinct, because in if they have the same number of this statement is incorrect. Why? Because there are not at least two of that one, because if they are the in the independent, like here we have a result, if they are subspaces of that one, then the dimension must be equal to 3. So these are some results regarding that one is, and then there are some topics of a row space and column space, which we also need to see over there. For example, if we have a any metric m cross n, which has the entries in the form of a rows and columns, then we can say about R1 first row, R2 second row, up to Rn. These are the rows of a matrix. Uh, and C1, C2, if we just take like the columns of that metric, it's called column vectors of a metric A. And so these are some usual and trivial part of that one. So the important thing is that if A is any n cross m metric, then the subspace of Rn spanned by the row vectors of A is called row space of A, and the subspace of Rm spanned by the column vector is called the column space of A. And similarly, the homogeneous, if in case of a homogeneous system, which is the solution space of a homogeneous system, which is a subspace of Rn, is called null space. So this we already saw that the solution space of a homogeneous system is a vector space, and we call it a null space. So there are the three things: the row space, column space, and the null space. Null space is actually the solutions of a homogeneous system. And then here there is an important theorem regarding the linear system, that if Ax equal to B is a linear system, and then such a system is consistent if and only if B is in the column space of A, or B can be expressed as a linear combinations of its columns. So this is the interesting and important part of that one. For example, if you find the solution of this homogeneous system, this non-homogeneous system, or if there is homogeneous, then still fine. But like since the right hand side, the B is non-zero, so we can write B as a linear combinations of the with the columns of a metric A, like column space of that one. For instance, if we put the 2 minus 1 plus 3 and write as a linear combination, then it will becomes the column vector of Ax equal to B. Like B can be represent as a columns, the linear combinations with the column space of A, metric A. So this is the interesting and important thing. One can see that these are always hold for that case. And then one can find the basis for a null space. We know that null space is a solution of a homogeneous system. The null space is actually the subspace, which is the solution space of a homogeneous system. And this is always a vector space, and the solution of a homogeneous system is called null space. And we can find its basis, like if you find out the solutions, then we can find V1, V2, V3, and then these threes are the basis for a this null space. And one can see that nullity is 3 because there are the three vectors. So dimension of a null space is called nullity. So basis of a row space and column space, one can figure out that just need to write them into the echelon form, reduced echelon form or echelon form. Then if we see that how many rows are independent or so how many rows are non-zeros in that, which is also give us a rank of the metric. So if you can see that the first three rows are non-zeros, it means the fourth row will becomes is eliminate with 0, 0, 0. Why? Because these three rows are independent to each other, which gives us the entries which are independent. So it means that there are only three rows are independent to each other, and one can see that R1, R2, R3 is the basis of a row space, because it means these if these three rows are sufficient to generate the first three or four rows. The rows of a matrix can be generated with these three rows R1, R2, R3. And similarly, one can see that how many if we apply the elementary row operation on that, so one can see that here it will gives us some of its non-zero the non-zero columns like first, second, and even the fourth, because these one can see that they have a leading ones, and with the help with having the leading ones of that one are the independent columns. So as they are independent, so it means these three are the basis of a column space, because these three can generate the other two as well. So all five can be generated with C1, C2, and C4. So these are called the basis of a row space and column space. So similarly, one can find the basis of a row space by reduced echelon form. So here you can apply the elementary row operation, and you can see that if the first three rows are non-zero, then it means these three rows are the basis of a row space. And the basis of a row space is called rank, as well as the number of non-zero rows in a echelon form is called a rank. So here the dimension is 3. Why? Because there are 1, 2, 3, three non-zero rows, and this 3 is all the if the dimension is 3 of a row space, so we call it a rank. So rank is 3. It means. Similarly, the find the basis of a column space by elementary row operation. So we just need to write as a apply the elementary row operation and see that where are the leading ones. So as we saw that the leading ones are over here. So it means that in there are the three leading ones in that. So there are it means there are three independent columns of that one. So the column space contains three vectors, and dimension of a column space is 3. So here these are also the some find the basis of a subspace of R5 spanned by these vectors. So if you find the basis of a R5 like which can be generated with these vectors, so apply the just write into the matrices form of in the columns, and then apply the elementary row operation. You need to check that which one row will become 0, and which three rows are non-zeros. If the all rows are non-zero, then it means all rows are independent to each other. Because echelon form is very important. Echelon form always tell us that how many rows are independent. And here, if we get the three rows are independent, then it means the basis will be 3, because these threes are independent and can span the all the four of that. So since here, if suppose if the two rows will become 0 from that, and only the two rows will becomes non-zero, then it means the two rows are sufficient to generate the other twos, and in that case the basis will be 2, the first two vectors. So here as the last row will become 0, so one can see that the rank is 3, and if the rank is 3, then it means the rows the of a this vector space that can be generated with these 5 its bases are the three vectors. So either you can write these threes, or you can also write those three rows which are non-zeros. they are still the basis for that one. And so the basis of a row space can be find out with the many methods, but it's important to apply the elementary row operation and write into the reduced echelon form, and then we can see that what are the row spaces. So transpose, if you take its transpose, then it will becomes a column space, and just take its transpose and one can write into the row space. So both are equally in form of that. So it's up to us that which method we can use and apply the dimension of a row space and the dimension of a column space. Basis and linear combination. Like if we have V1, V2, V3, V4, V5, find the subset of a vector space that comes from the basis for the space spanned by these vectors. So again, if we write them in either in a row form or a column form, and then we need to apply the elementary row operation to check that which of the following rows are independent, and which if the rows have independent, then it means they must have a leading ones over there. So the leading one entries are in W1, W2, and W4. It means these fours are independent columns. So we conclude that the basis of a the basis is of a basis is W1, W2, W4, which generates the all vectors of all the class of all vectors generated by V1, V2, V3, and V4, V5. So this is the method for that one. And here, this also tell us that we need to apply the either elementary row operation to make it into the reduced echelon form to get the number of bases for that. So after that, there is a one interesting method which is called the fundamental theorem of a matrix space. So this is also called the fundamental theorem of a linear algebra. Uh, it based on the nullity and rank. Rank is actually tell us that how many number of rows in echelon form, because in echelon form always gives us that how many rows are non-zeros which are independent to each other. So the number of non-zero rows, if they are independent, then it generates the vector space, and that's are the basis. And the number of non-zero rows which generates the column space is called the rank, because the rank is also number of non-zero rows. So in echelon form. And nullity is, we know that nullity is the solution of a homogeneous system. Solution space, the dimension nullity is the dimension of a solution space of homogeneous system, which is also called nullity is also called the number of elements in the basis set for a null space. We know that null space is actually the solution of a homogeneous system. The solution set of a homogeneous system generates a vector space and whose dimension is called nullity. So for every metric, we know that if A is a metric, then the row space and column space of a matrix have the same dimension. Like if because they either they have how many rows are linearly independent and how many leading ones of over that one is. So both are equivalent and both will give us the same dimension. Like row space will gives us a rank, and the number of leaders in that one gives us a vectors of a column space, but both have the same number of elements, so it means dimensions of both are the same. And recall that the common dimension of a row space and column space of a metric is called rank. Rank means the number of non-zero rows in a echelon form, and also it gives us the how many linearly independent rows or how many linearly independent columns in a matrix A, and it's denoted with the rank of A. And the dimension, since we know that dimension of a null space is called a nullity, like if we found the solution of a homogeneous system, then its dimension is always called a nullity of that. So dimension of a so we can find the nullity and rank of any metric. So if we have this metric, we apply the elementary row operation to check that how many rows are linearly independent or how many rows are non-zeros. So if you apply elementary row operation or reduce row echelon form, So you will get these two rows. It means there are two rows which have the leading ones, or there are two rows which are non-zeros. So it means the dimension of a row space is 2, hence rank is 2. The rank also you can find in a short way, you can see how many number of non-zero rows in a echelon form. Then the another thing is the find the solution of a homogeneous system. If you find the solution of a homogeneous system, then the solution of homogeneous system is always a vector space, and its dimension is it have at some dimension, and the number of elements in dimension in a number of elements in a basis set of a homogeneous system is called a nullity. So just find the basis for that one. So it means we need to apply the solution of a homogeneous system. So if you find the solution of a homogeneous system, it will gives you the parametric solutions. If you separable the parameter of that one, so then we will get 1, 2, 3, 4, 4 vectors that generate the solution of a homogeneous system. So these, if there are 4 vectors, then it means dimension of a solution of a homogeneous system uh, is 4, and these 4 are actually the basis of a solution of a homogeneous system. And just recall that solution of a homogeneous system is a vector space which is called null space, and the number of elements in a basis set of a homogeneous system is called nullity. It means nullity is equal to 4. And this gives us one idea when we read the linear algebra, that there is a 4 over here, and here the rank is 2 because number of non-zero rows are 2. So 2 plus 4 is 6. And how many columns? 1, 2, 3, 4, 5, 6. There are 6 columns, or there are 6 column vectors over that. So this gives us one information, that the rank mean number of non-zero rows plus nullity, number of vectors in a solution space of homogeneous system, is always equal to the number of columns of a metric, which is 6 in that case, like 4 plus 2 plus 4 is 6. So this is called the fundamental theorem. And remember that rank of A is always the minimum of number of rows or number of columns of a metric. So this gives us a one standard formula or standard rule for dimension theorem of a, it's also called the dimension theorem of a matrices, or fundamental theorem of a linear algebra, means nullity of A plus rank of A is equal to n. Mean if you have any metric A with n columns, n number of columns, then rank mean number of non-zero rows in echelon form, or number of leading variables in metric A, and plus the nullity means solutions, number of elements in a solution space of a homogeneous system, and which is also the basis of a homogeneous solution of a homogeneous system, nullity. So nullity plus rank is equal to n, the number of column of a metric A. So that is the standard and fundamental theorem, and one can always be check. And similarly, if you know what is the rank, and if if the rank is 2, then it means nullity is equal to 4 in that case, because the total is will becomes number of columns, like number of columns is equal to the 6. This fundamental theorem we can always be verify. For instance, if someone asks you that in a metric A there are two non-zero rows, then what will be the nullity of that? Whenever A has say 4 rows and 6 columns. Like if A has 6 columns and rank is 2, then it means nullity is, one can say that nullity of A is equal to 6 minus 2, which is equal to the 4. So one can be verify this thing in that one. So this fundamental theorem is very important. So the rank, we know that number of non-zero rows in echelon form, or the rank is also the number of leading variables in the general solutions of Ax equal to 0. So rank is very important because it's, we can get it with a basic elementary row operation. So elementary row operation is very, very important, which always tell us that how many rows are independent to each other. If there is any row which is becomes dependent on the other rows, it will automatically become 0 by elementary row operation. And the nullity of A is the number of parameters in the general solution of Ax equal to 0. Like it's a dimension of a solution space of homogeneous system, or dimension of a number of element dimension of the null space, because the solution of a homogeneous system is also called a null space. So here this is the problem, as I told you, that if the number of parameters in a general solution, like if you have a metric, A is a metric 5 cross 7, it means 5 rows and 7 columns. And suppose its rank is 3, then what will be the nullity of that? So nullity of that one is equal to n minus rank of A, mean number of columns which are 7, and the rank, since rank is 3, number of non-zero rows are 3, so 7 minus 3 equal to the 4. It means there are the 4 parameters, or the four, the nullity is 4, means the dimension of a homogeneous solution of homogeneous system is 4. And then the followings are equivalent in that case, like if A is invertible metric, like A has if A inverse exists, then Ax equal to 0 has only trivial solution, which is 0 0. And again, you know that if it has a trivial solution, then the solution is still a vector space, because 0 solution is a vector space or subspace whose dimension is also 0. And it can be reduced to A can be reduced to the identity metric because it's a square metric. And A can be expressed as a product of elementary matrix, which I hope you saw in the linear algebra 1. And Ax equal to B is consistent for every metric, every column n cross 1 metric B, or like every column metric B. It is consistent because if invertible, Ax equal to B has a unique solution. It has exactly one solution, and because of consistent, it means it has a exactly one solution, and determinant of A in that case is not equal to 0, because A is invertible. And the column vector of A is linearly independent. Row vector of A is also linearly independent. All the rows are independent, because if you apply elementary operation, they becomes a identity metric. And in the identity metric, we know the rank is equal to n, non-zero number of non-zero rows are n, and all the columns leading ones have the leading ones, so they have again n number of vectors over there. And it means the row vectors of the column vectors of A form a basis of Rn. Similarly, the row vectors of A forms a basis for Rn. The rank A has rank n because all rows are non-zeros. So rank n mean all the rows are non-zeros. So n number of rows are non-zeros. And nullity, A has nullity 0. The dimension of a solution space of Ax equal to 0 is 0, because it have a 0 vector only, which is the solution. So we know that dimension of a 0 space is 0. So it means nullity is 0. So these are the some basics results in that one. So these are the important thing. If you have any question, you can ask your question, but let us comes to some problems uh, related to that one. For instance, discuss how the rank of A varies with T. Like if T is any parameter, and we can see that how it will affect uh, something on that. So I have one problem which is I have already shared on the in the website of a PyModules MAT2611. For instance, find values of R and S for which it affect when A has rank 1 and A has rank 2. If so, then find the values of that one. Now, the important thing is that we need to apply the elementary row operation over here. And if we apply the elementary row operation, for example, we can see that here we have 0, so we can interchange that one and apply the elementary row operation over here. Like 1 by, we can make it the as 0 comes over here, then we apply again the uh, 3 can be make as a 1 as a leading one. How? Just divide 1 by 3. So then if this is the leading one, then we can apply elementary operation to make this 2 as a 0, and also multiply uh, this one with r plus 2 and subtract with the that number with r3. So then in this way we will get this form, which is the elementary, which is in a echelon form. So when we have this echelon form, so we can see that what will be the rank of that matrix. Rank means number of non-zero rows. So we know the leading one is here, leading one is here. So the first thing is, what is the minimal rank? Is the rank can one? Rank 1 means only one row is non-zero. But here this row is have the 1. So this rows can never be 1. This row can never be 1. So it means the rank of A is never 1. It can be at least 2. And if the rank will becomes 2, so here it is mentioned that the rank of A cannot exist because it has at least two rows that are non-zeros. And for rank 2, if we have rank 2, then it means there are two non-zero rows, then other rows are 0. In that case, this R minus 2 must be 0, S minus 1 also must be 0. And if r minus s, sorry, r minus 2 equal to 0 and s minus 1 equal to 0, this gives the value of r is 2 and the value of s equal to 1. So this means that the rank of rank is never 1, and the rank of metric A is 2 whenever r is equal to 2 and s equal to 1. You can check it that this is in the clown form. If you put r equal to 2 and s equal to 1, then this row will become 0, this row will become 0, then rank of A, rank of metric A will becomes 2 in that case. So this is the example we can see in that direction. So similarly, in this problem, we need to apply the elementary row operation because rank will tell us that how many non-zero rows in a echelon form. So then you can see that what will be the rank and how it will be affect for the values of t's. For instance, if t has b plus minus 1 or whatever, so you can figure out that one in the both part A and B. In problem number 19, here you have a two subspaces of R4 is available. Then find the dimension of U and V. We already know that how to find the basis of a vector space or subspaces. So when we find the basis, then we can see that how many number of elements in a basis set. So the number of element of basis set in U of a U is the dimension of U, and the number of elements in the dimension of V is the number of elements in a basis set of a uh, vector space V is the dimension of V. We can find the number, but it can be less than 4. It must be less than 4 because the whole space has the 4 of that. So this we already discussed in the previous lesson. So how to find basis? So just count the number of element in a basis. So that gives you the dimensions of both vector spaces or subspaces of R4. The next thing is that find the nullity and rank of a metric A. Here A is a 5. We have in a A there are 5 rows and 5 columns. So in that case, we can just apply the elementary row operation over here, and then we can check that how many rows are non-zeros. So if the number of non-zeros are suppose maybe 3 or 4 or whatever, so that will gives us a rank. It means that rows are sufficient to generate the all rows of a matrix A, and that is called the rank, mean number of non-zero rows. And then if you find the solutions of a homogeneous system, then it will gives you the nullity. So the nullity we can find it, and as we know that since there are the 5 columns in this metric, so it means nullity plus rank is must be equal to 5. If the rank is 2, then nullity will be 3, that equal to 5. If rank is 1, then nullity must be 4 because 1 plus 4 is 5. And this is the technique, and this is always true. So that's why one can verify this formula of a dimension theorem of a matrix, which is also called the fundamental theorem of a linear algebra. So this is the lesson or today lesson. So if you have any question, you can ask your question. Yes, please. Yes, you can ask your question one by one.
Okay, say on problem 20, is it necessary to reduce to a reduced raw echelon form or is fine if you leave it in raw echelon form?
Yes, good question. So, if it's in a echelon form, then it is sufficient also because if you comes towards to apply more effort in the reduced echelon form, then it will becomes more nice. But echelon form and reduced echelon form both are both are important. And if you use any of that, like if you stop at echelon form, then it's still sufficient. The sufficient thing is one, and one thing is if you want to make it more clarification, then comes towards apply some more operations, make the all the leading ones and the rest of entries must be equal to the leading ones, and all the other entries will be zero unless the rows is zero. So then it will become both like the answer is, I think you understand that if you stop at echelon form only, then it is sufficient. But if you apply the more steps and apply get it, and you can get it reduced echelon form, then it's still fine.
Okay, thank you, sir.
Okay. Any other question? Yes, please. Yes, you can ask your question. First unmute, then you can ask your question. Otherwise, you can type your question. Okay, question number one of the assignment, like if you see, I have already described the coordinate vectors of P. So in previous lesson, we saw that what are the coordinate vectors? Coordinate vectors are actually just the constant terms of any vectors. Like if you write as in a linear combination, then there will be some constants. So if you write that constant into the form of a vector, so that is called the coordinate vector. And it's we already discussed that one. So here one example is already shown that how to find this PS, like for the if there is a standard basis, like we know that 1x, x square, xn, these are the standard basis, and it have a n plus 1 elements, because 1 is also x power 0 mean 1 x square up to xn. So there are how many elements? 1 x square up to xn. So n plus 1 element. So it means the basis is n plus 1. So but the coordinate vectors are the vector c0, c1, c2 up to cn. So we can find that coefficients. And here I describe you that if you solve anything or of that one, so A, B, C, D. In case of a standard basis, it's very easy because it's already appearing that what are the elements. If we have here 1 plus 2x plus 3x square, then it means 1, 2, and 3. 1, 2, 3 just put, and it's a coordinate vector. But in case if it's not straightforward, like this example here, I can show you one example which I hope you already saw, that these are not standard bases of R3. But if you find the any vector with the help of that one, so we can apply this method to get the coefficient C1, C2, and C3. With the help of that, you can find out the values of C1, C2, C3 and write them into the form of a vector, and that vector is called the coordinate vector. For instance, in this problem, you just need to write this P, like 3 plus 4x plus 2x square is equal to C1 times 1 plus x put into the bracket, plus C2 times 1 plus x square close bracket, then plus C3 times again open bracket with x plus x square bracket close. Then if you write them separable and take the coefficients of constant, coefficients of x, and coefficients of x square, this gives you some form of a linear system. And you need to find the values of a C1, C2, and C3. Then if you write these C1, C2, C3 into the form of a any column, any vector, then that is actually the coordinate vector of the given vector P. But in case if it's suppose if P1, P2, P3 are suppose they are standard, like P1 is only 1, P2 is x, P3 is x square, then in that case your coordinate vector will be 3, 4, and 2. Like just write the 3, 4, 2 into the form of a vector, then it is called the coordinate vector of P. But here you just need to do some more steps, like just take P equal to C1, P1 plus C2, P2 plus C3, P3, and then need to find the values of C1, C2, C3, and then write as a vector C1, C2, C3 in the form of a vector, then that vector is the coordinate vector of P. So that is the method for that question.
So what I have a problem with is how do I write it in a matrix form? Because it's now two, like one plus x, then it would be at the corner and then another one at the corner, but it would be one line, not like four rows or four columns and four rows.
Okay, suppose here you have a P, which is something like 2 plus say 3x minus 4x square. This is our polynomial P. And suppose we have a basis set. Like if I have a basis of a P2 is a P1, which is something like that x say 1 plus x. Suppose this is P1. P2 is the suppose I have 1 minus x square. Suppose this one is P2, and let's see, P3 is the another element of a basis set, which is say x plus 2x square. And suppose that this P1, P2, P3 is the basis of a polynomial of degree 2, and we want to find the coordinate vector of this P. Then definitely if these are bases, then they can generate every element of 2 cross every element of a uh, every element of a vector space of a polynomial of degree 2. So mean every polynomial they can be generated with P1 and P2 and P3. So we need to find the coordinate vector in that case. So what we need to do is that we just need to write the P is equal to C1 P1 plus the C2 times P2, and then plus the C3 times P3. Okay, like P3, and need to find what is the values of a P1, P2, P3. Here I can tell you that if you find the values of a P1, P2, P3, then your coordinate vector of this P, sometimes we denoted this with P and some S set over here, because this S is a basis set. Recall that this S is a basis set and it has the P1, P2 and P3. These are the actually the vectors of a basis set. So that's why we denoted it with P1, P2 and P3. So here the PS will be that vector which contains C1, C2 and C3. Our solution, question is that to find out the value of C1, C2, C3 and put over here that what are the values over here, like identifies these three values, like the first value, then second value, and the third value over here. But as I understand that what you are asking how to do that one, so as I tell you that just put the value P over here, like P is 2 plus 3x minus 4x square. Here you have this thing, and then that will be equal to, say, C1 is unknown, we need to find, but we know that what is the P1, which is 1 plus x, plus the C2. C2 is any unknown number, and here we can put the values of a x as P2, and then plus the C3 times the value of a P3, which is x plus 2x square. Now here, as I told you that we need to write this thing into the form of a here. This side will be the same. We just need to be stay over that and just need to apply some steps over here. Like as I told you that just need to compare the coefficients of that one. For instance, here if you multiply x with all of the entries, it means it will becomes c plus c1 plus c1x. Here it will become c1 minus sorry c2 minus c2 times x square, and here it will becomes c3x and plus 2 times c3x square. Here we know that on the left side we have the number without x, number with x, and number with x square. And here we have some constants with x and x square entries. So we need to be write them and we want to compare the coefficients. So here we can also make a compare the coefficient, but we can also do something simple way. In a simple way, like if just I just take the common over here, and we know that the constant is 2 over here, but the constant over here is we have what is the constant? Here we have C1 is constant and plus C2. Like these are without X. So we just make these two in the one side. Then for the X, we know that X is over here, X is also over here. And here, if we see about the X, so if we just take the common X from here, and what are the rest of entries? So it will be the C1 plus C3. Then plus for the x square, we can see that if we see about the x square, then here we have some entries. For example, minus the minus c2, and then there is another plus 2c3, then plus 2 times c3 we have, and just try deleting the rest of things from there. So what we do is that just make separate the x, the constants on one side, the constant coefficients of a x on one side and the constant coefficients of x here on that side, because we want to make it same. Like here there are the constant entries without x, the constants of x, and then constants of x square or the scalars of x square. Then here our objective is to find the values of a c1, c2, c3, which is our the prime objective. So what you need to do is that you just need to compare coefficients of 1, x, and x square. So if you compare the coefficients of that, then you can find the solution of a C1, C2, C3. Like we know the one mean constant is 1 on that side, and constant by default 1 is, if there is nothing, then there will be 1. It means it will gives us what, for example, for the constant comparing, if there is a 2 on that side, on the other hand side, it's only the C1 plus C2. This gives you first equation. The compare the coefficient of x here on from the both sides. So here there is a 3 on the left side, and on the right hand side we have what, x1 plus x c1 plus c3. And similarly for the coefficients of x square, which is the minus 4 on the left side, and on the right hand side it's minus c2 plus 2 times the c3. So look, this will becomes a linear system. We can solve it for any method of a linear algebra. Then we can find the values of a C1, C2, and C3. And then just put over here and you can check it later on. If you put C1, C2, C3 and solve them, then it will exactly will becomes the same vector like 2 plus 3x minus 4x square. But you remember that this vector will be generated with these C1, C2, C3s. Like if you put over here, it means this P1, P2, P3s are generating this P, because these P1, P2, P3 are the basis of a polynomial of degree 2.
Thank you, sir. I understand now.
Any other question? Yeah, problem number 18, as I show you one example, and I told you that apply the elementary row operation. and then see what is the rank of A. Like if the rank is 1, rank is 2, rank is 3, for the basis of that, you can find out the values of a t. For example, if there are two variables, two constants, or the two values r and s, apply the elementary row operation, and then you can see that what is the rank. Rank means number of non-zero rows in echelon form or reduced echelon form. You can stop anywhere, and then if the rank is equal to 2, it means two rows are non-zeros and the rest of rows are zeros. So you need to put r. How to make these two rows zero? If you take r minus 2 equal to 0 and s minus 1 equal to 0. It means if rank is 2, then r is 2 and s equal to 1. So this is the method which he already described. And the rank of 1 is not possible in that case because the rank, there are already two non-zero rows which are independent to each other. So this is the method of a rank. I will also upload this lesson on the upload on that, and you can follow the things if you have any query. Any other question? Yes, you can. For the problem number 17, yes, like as you know, here you will get the this one. So you can apply any method to find out the solutions. You can just write into the matrix form. This is also good that if you put, say, the find C1, C2, C3, you can write into the matrix form and solve this linear system. The matrix will becomes, the 1 to 0. Then similarly, the other entries is so 1, 1, 0, 1, 0, 1, minus 1, 0, 2, and the right hand side is 2, 3, minus 4. And it will becomes a linear system. The linear matrices is also solutions of a matrices also give you a linear form of that, and you apply the elementary row operation to solve it. You can apply any method, and it's fine that you can write them into the matrix form and get solutions by either apply the elementary operation or Gauss-Jordan method. You can use Cramer rule even. So there will be the many other nice methods of a linear algebra as well. There is also the one rule which is based on the eigenvalues. So which I hope you not saw now, but you can also apply the A inverse method, invertible metric, and get its solutions if the metric is invertible. So you can use any method. The objective is to find a solution of this to get the values of C1, C2, C3. Okay, if there is no question, then we can stop session over here. If you have any question, then still you can ask your question.
Okay,
Is there any?
sir.
Yes,
Yes,
please.
I have. Okay, I'm not sure if they asked this question because I have a network problem. On problem 18, can we solve that question using the determinant and then
No, no,
that?
no. Here, when we apply the rank, so rank is actually based on how many rows are independent. So this is only based, you can use here elementary row operation. No determinant is, there is no technique for that. So only the elementary row operation is using that to find the rank, because rank is giving you the number of independent rows. Okay, many best wishes. I hope it's clear to you. Okay, dear students, have a good day and best wishes. Goodbye.
There is no light.
Sorry, what you are saying?